Okay, so today we're going to prove what I spoke about in the last video, namely that there's a unique minimal inductive set. This is the same thing as saying that for all other inductive sets, the minimal inductive set will be a subset of the inductive set. So recall a set A is inductive if the empty set is in A, and for all x in A, x union the set containing itself is also in A. So these are the two conditions that inductive sets have to satisfy. So in order to do this, we're going to first state a claim. So claim, given a set fancy F, the intersection of F exists. And what do I mean by this? Where we have that X is in the intersection if and only if for all sets in F, X is in that set. So the example, if X is the set, if X is the set 0 to 1, the closed interval from 0 to 1, and then X is the set from 1/2 to 3/2, then the intersection of F is going to be equal to 1/2 to 1, right? Because the two sets, these two sets only have in common the elements that are between these two, between 1/2 and 1. Okay, so how do we prove that this set exists? Oh, sorry, the F is supposed to be non-empty. Okay, so proof, given F non-empty, that means by definition there exists an A in F. By comprehension, define B to be the set of all things in A such that for all K in F, X is in K. And this is going to be equal to what the intersection of F is. And why is that? Well, if something is in B, something's in B, then that means that, and you take any element of F, it's going to be in F by definition. And if you take any element, the intersection of F, that means it's in every element of F. Because A is a subset, or A is an element of F, this condition is redundant. So these two things are in fact equal to each other. Okay, so now that we have our fact that intersections of sets exist, we can state the first, I guess, lemma, or I'll just say it's a claim. Claim 1. The first claim, given F, where F is a non-empty set of inductive sets, then the intersection is also inductive. Okay, so how do we prove this? Okay, so the first thing is that the set is, and we need to, this is our goal, that the empty set is in F. So this is the goal. Well, we'd say something like, let A be an element of F. Then we know this holds because A is inductive. So in order for the empty set to be in the intersection, it has to be in every single element of F. And that's true simply because every element of F is inductive. So the second part is we need to demonstrate, so the goal, if X is in the intersection, then so is the union So how do we do this? So we say assume X is in the intersection. So for all A and F, X is in A. Since A is inductive, for all A and F, we have exactly what we want. We have that the successor, so A union the second X union the second chaining itself, is in A for all A and F. But then this is exactly what it means for X union the set containing X to be in the intersection. So then we're done. Now let's claim 1. Okay, so what we can, so the axiom of infinity, which we talked about last time, that means, so axiom of infinity if you remember, that says that there exists an inductive set. There exists an inductive set I. Okay, so what we're going to do now is we're going to create the minimal set by recognizing that all we really need is that there is at least one inductive set. So how do we do this? Define fancy F to be equal to the set of all elements, the elements of the power set of I, such that J is inductive. So in other words, this is the collection of all inductive subsets of I. And then what we're going to do is define omega to be the intersection of F. So I talked about in the last video, we denote this minimal inductive set by omega. So I'm going to do that here. And this intersection of all inductive sets of I is precisely going to be what we mean by omega. So by claim 1, omega is inductive. So the next step we need to show, so claim 2, if we have any other inductive set, then omega is a subset of J. So proof, how do we do this? Assume J is inductive, and we need to demonstrate that omega is a subset of J. So assume that we have an element of omega. Omega is again the intersection, which is the set of all x, such that for all A and F, x is in A. Now, because J is inductive, and I is inductive, and I was the set that we assumed exists by the axiom of infinity, we know that J intersect I is inductive. And why do we know this? Well, I comma J is going to be a set by pairing, and that's a set. That's a non-empty set, so we can take its intersection. And that's precisely going to be what this is. And we know that this is inductive. Well, there's something further than this. We know that I intersect J is a subset of I. And why is this important? Recall that F was the set of all subsets of I, such that the set of all inductive subsets of I. Well, what does this mean? We know that J intersect I is a subset of I. This implies that J intersect I is going to be in F, because it's inductive and it's a subset of I. Well, now we're almost done. So we know that X was in omega, which is equal to the intersection of F. What does this mean? This means that it was in every single element, this means that X was in every inductive set, in every inductive subset of I. So in particular, X is in J intersect I. But this by definition means that X is in J. So we have this by definition. So that was claim 2. The third one, the third step we need to show that this set that we just defined, omega, is unique. So claim 3. If omega prime is inductive and omega prime is a subset of omega, then they're in fact equal to each other. Well, how do we prove this? Well, because omega is by our previous claim, because omega prime is inductive, we have from the previous claim that omega is a subset of omega prime. But we also have that omega, by assumption, that omega prime is a subset of omega. This means by definition that omega is equal to omega prime. and then we'd be done. We've demonstrated that there exists a unique minimal inductive set, which we're going to be calling omega. And again, this omega is really what we should be, our intuition about what omega is really the natural numbers. So it'd be the counting numbers 0, 1, 2, 3, etc. So in the next video, I'd like to talk about the replacement schema, and then we'll start talking about the axiom of choice.